Hi, I'm Joel Esposito from the United States Naval Academy. And today, I'll talk a little bit about this idea that came to me from my work in big data and AI, which is that when we work in these high dimensional spaces, it's really important to take into account the geometry of them because sometimes that has algorithmic implementations. So my idea for this talk was to take a look at what happens in algorithms like RRT and PRM when we try to run those in very high dimensional space. And one example might be planning for a humanoid task like this one. You can easily imagine there's 40 or more degrees of freedom here. Other examples of high dimensional spaces could include redundant manipulators, continuum or soft robotics, large swarms, and some techniques from motion planning that have applied to the complicated protein folding problem. So the part of this I really want to focus on is sampling. So one very common sampling scheme is to use a uniform distribution to sample along each dimension. So in 2D, for example, if you're trying to fill this square workspace here with samples, you would generate a uniform distribution on the x-axis, uniform on the y, and use that to make vector coordinates of all these points here. And while that looks really quite uniform in visually to the eye, if you made a plot of the distance of each of these dots to the origin, and you made a histogram, you would see right away that even in 2D, it's not exactly uniform. In fact, there's many more samples at this mid-range of distances, and very few near the origin, and very few out near the corners. And that has something to do with the shape of the square, as well as the fact that you're summing up several random variables. And concentration of measure is the term that predicts that as the dimension goes up, that these measures will concentrate even tighter. So for example, in 10 dimensions, hypercube workspace, if you made that same plot, it would look more and more like a normal distribution, even though there's a uniform distribution used to generate each of the coordinates individually. Collectively, they start to concentrate. And it becomes really extreme at higher dimensions. So you can see in 50 dimensions how tightly concentrated all the samples are in a small area. So that has some interesting implications. I'll talk about 4 of them here today. So the first one is that what that means is that almost all the samples with high probability are really just sitting on this thin-shelled surface of this hypersphere sitting inside this 50-dimensional hypercube, which is the workspace. Meaning that there's basically 0 probability of generating any samples near the origin, and there's 0 probability of generating any samples in the corner of the workspace, which might be important areas that you want to explore for your application. If we could visualize it in 2D, the samples would look something like this on the right. And that's important because we all know that the vertex distribution will approach the sampling distribution in the limit. The second fact that I think is interesting to explore is the choice of an initial vertex. Very often we seed the tree with one vertex that's not generated at random that we arbitrarily place. And it turns out that the placement of this vertex can have huge implications for the growth of the tree. So for example, I might decide to put a vertex at the origin, but that's an interesting choice because there's virtually 0 probability, if you recall, of generating one there by chance. What happens in that case is that with high probability, it will be the nearest neighbor to every other sample that's generated. And you'll start to generate a tree or grow a tree that becomes effectively star-shaped, meaning that they have that one root there at the origin, and every other vertex becomes a leaf of that. And that's not usually the type of tree that we want to generate. A third implication is the role of the parameter Dmax in many sample-based algorithms. This is a threshold. It says if 2 vertices are closer than this value, then we try to establish a connection. And the purpose of it is we want to make it big enough to connect the graph, but not so big that we attempt an all pairs collision check, because that's very expensive. But you can see, because this is so tightly clustered, there's a narrow range of meaningful values for Dmax. If we go too small on Dmax, none of the vertices are going to be within that distance. So if we go anywhere between 0 and 2 in this example, we'll get an empty graph. No vertices will be connected because they're all further apart than that. And if we go anything over about 3.5 all the way up to 7, we are going to attempt to connect every single node in this tree, which is going to be computationally expensive and not what's desirable in practice. So it's a very narrow range of values. The fourth interesting fact is that the nearest neighbor, which is often how we choose which nodes to collision check or expand, it becomes less and less meaningful in high dimensions. The Euclidean distance has what's called poor contrast, which means the difference between the closest and the furthest nodes gets smaller and smaller. Some people might propose, hey, use a approximate nearest neighbor algorithm because it could run faster in higher dimensions. But in fact, that's a worse thing because say your algorithm for nearest neighbor is off by say plus or minus %. Well, you know what? In that case, that means virtually all the nodes are within that range. So in that case, a random vertex might be almost as good and way cheaper to generate than one through a nearest neighbor algorithm. So I know that was really fast. I kind of felt a little a clickbait or gimmicky saying that so quickly, but I would encourage you to read my paper for more details about some of the interesting facts of growing these kind of roadmaps in high dimensional spaces. Thanks for listening.